Welcome back, guys. Now we go for, we're going to discuss the details on how to define the solution for our primal dual path following interior point method. This solution that we are going to use in our toy, which is a linear optimization problem, as you guys remember, is based on this book, actually on this chapter, Operations, Research Models and Methods. It's a book, and the chapter is LP Methods as for interior point methods. It's a chapter by Jensen and Bard, published in 2002. And it's quite interesting as a toy, as an introduction to interior point methods. I suggest you guys to look for this chapter and study it too. It's quite an interesting way of introducing the approach. So at this point, we have our primal and our dual problem. So both problems are here, as you guys can see. Of course, this primal is a maximization problem in terms of x1 and x2. This is a minimization problem in terms of pi1 and pi2. What I need to do at this point is I need to remove those inequalities from my constraints, except the variables themselves, something that we are going to solve later. So our first step is I need this constraint to be smaller than or equal to 8. So somehow, what happens if this number formed by 2x1 plus x2 is smaller? I need to sum a slack variable. So I will have something like this, plus x3. Going back, I will sum up x3 over here, as you can see, to have 8 as output. What happens if this constraint is smaller than 6? I need to sum up another slack variable x4 to make it equal to 6. That's what's happening here. Plus x4. Of course, x3 and x4 must be greater than or equal to 0. Otherwise, I would be, if it were negative, I would be subtracting a value from this part of my previous inequation or some value from this, making it like even far from 8 and 6. In my dual problem, I have inequations in terms of greater than or equal in this particular scenario. If I have something greater than or equal, of course I need to subtract something from this side. Subtract a given slack variable, and the slack variable is going to be greater than or equal to 0. And here the same, I need to subtract it. You guys will see that I decided to subtract z1 over here, making this equal to 2. And I subtracted z2 over here, making it equal to 3. z1 and z2 must be greater than or equal to 0 in this scenario to make those two equations hold. Now equations, of course, because they were inequations in the form of greater than or equal to. I need to subtract because something might be greater, so I need to subtract to make it equal to 2. And here it is greater, I need to subtract. And remember, my slack variables are always greater than or equal to 0. So there is no problem about subtracting here, because I'm not going to maybe subtract a negative number and make it like even greater than 2. That's not going to happen here. In this chapter, the authors also decided to change the variables pi1 and pi2. what they did was exactly this. They decided to call pi1 as z3 and pi2 as z4. What they did, and we can do, or maybe we could just add here instead of z1, this could be pi3, and this could be pi4, as we did over here in our prime. But instead of that, they decided to completely change the variable from pi1 and pi2 to z3 and z4. So when I subtract, of course, my pi1 minus z3, which is, of course, greater than or equal 0, the same for z4, they are going to be equal 0. So I'm just looking for those variable constraints as if they were constraints in this form, as if they were some inequations like with several variables, but I'm just looking for pi1 that has to be greater than or equal to 0, so I subtract something that's positive, it's going to be equal to 0. And of course, pi2, it has to be greater than or equal to 0. When I subtract some positive value, I make it equal to 0. And I substituted all variables by z1, z2, slacks in terms of those constraints, and z3 and z4 in terms of those two variable constraints. Okay? We discussed before about slack variables, but what they do is basically add some relaxation in my problem. So I can find some solution having some value for my slack. If I have some relevant value for my slack, or even better, if my slack is different from 0, that basically means that I don't have I have like some spare value, like some remaining in my solution. I do not have like the perfect solution because I'm not completely touching my constraints as if those x3, x4, and all those here, z1, z2, z3, and z4 were equal to 0, of course. Another step, observe z. They were subtracted over here. Okay, this is just to remember. Because if we subtract the greatest possible value, we'll end up having an equality. That's why we're subtracting here z1 and z2, as I mentioned before. Okay. And of course here we needed to sum up x3 and x4 because we have like something that's smaller than or equal, so we need to be equal 8 and equal 6. So we need to sum up some positive value. So x3 and x4 are positive, greater than or equal to 0 at least. This is the solution for our problem. This is so interesting. Just pause the video, pay attention, look at the solution. You're going to see that from the primal space, we start with some initial solution. And at each iteration, we give a step. Like this was the step we took. Okay? This is going to be like the gradient of my objective function. So I'm walking towards a gradient. Walking towards a gradient. Walking towards a gradient. Walking again. And trying to get as close as possible to this point, which is my solution. But of course, I'm not going to touch it because I have a barrier here. We discussed about that before. From my dual space, this point here is exactly this point in my dual. So I will always have a counterpart in my dual. If I select a point in my dual, I'll have a counterpart in my primal. So I am at this point and this point. Of course, if I take this particular pi1 and pi2, this particular x1 and x2, and apply my problem, it will not satisfy my constraints. In what sense? Actually, slacks will be really, really great. I have like x3 equals, I don't know, 5, x4 equals 3, x1 minus, I don't know, like minus 5, xz2, and so on. What means that I haven't found the best solution for a linear problem, because I know that for a linear problem, I need to touch a vertex. Of course, for a convex optimization problem whose solution is in the middle, at the middle of my feasible set, I don't need to touch a vertex, but I have like other ways of verifying. But in this particular toy, yes, I know the solution is here. So I can measure how distant I am from the perfect solution. Next step. So at this point, we're going to give a general formulation for interior point methods while solving linear optimization problems. This general formulation can be used to solve any linear optimization problem. Of course, it takes more time than using the simplex method, which would just visit vortices and find the best solution. So it's not like a good idea to employ this in any kind of problem, but it's interesting to apply it on some problems, on few problems, at least to understand what's happening. Of course, here I'm just considering that C is a vector multiplied by X. Of course, C will have those coefficients as here. Like 2 and 3 is going to be my C vector. And X1 and X2 is going to be my X vector here. Of course, here we'll have also X3 and X4. When I have X3 and X4 over here, the corresponding coefficients will be multiplied by 0 because there is no x3 or x4 in my objective function. But they happen here, and they must be greater than or equal to 0. So, of course, you guys can see over here that all scalar elements in my x vector must be greater than or equal to 0. And my matrix A times X must be equals B. So A is the matrix composed by 2 X1. So coefficient is 2, coefficient is 1, coefficient is 1. Here, coefficient is 1, coefficient is 2. Oops, there is no X3, so coefficient is 0 for X3 and 0 for X4 here. And for X4, in this case, is 1. So my matrix will be 2, 1, 1, 0, and 1, 2, 0, 1. Okay? That's my matrix A. And my B in this particular problem, of course, it will be 8 and 6. And on this side, we have the same, of course. 8 and 6 for my coefficients. Take a look. 8 and 6 will be my my B. Pi will contain pi 1 and pi 2 because Z is just a different set, as you can see. So pi product by matrix A, what is the same as the transpose of A multiplied by pi, minus Z, and this Z will contain Z1, Z2, Z3, and Z4 equals C. And you guys know that in my case over here, C is going to be 2 and 3. And 0, 0, because we also have to ensure those two constraints over here to be equal to 0. Okay? That's really nice. So this general formulation can be applied in any kind of linear optimization problem. You can adapt it to your problem and solve it. Okay? So just to give another step, we need the barriers at this point. The barriers are going to affect the way we wrote those two problems over here. And you're going to see at this point. How are the barriers? The barriers, for example, look like this. Consider I have like some input variable here. I called it time, but it could be any kind of value, any kind of variable, sorry. And I have a minimization problem. So if I have a minimization problem and my variable time has a value equals 0, I will assume this value to sum up in my objective function. What happens if my variable time is equals to 20? It's going to be greater. What happens if it's like 5? It's going to be even greater. What happens if it's really close to 0? It tends to infinity. So when I sum up this, the result of this barrier in my objective function, I am changing, I am penalizing my solution. So the closer I am to this 0, the greatest is going to be the value of something that I'm trying to minimize. So it's not good to go too close to 0. Okay, that's really nice. How those barriers are constructed. They are constructed using log functions, as you can see here. So if I open a Guinea plot over here, just plot like plot of minus log of some x, that's going to be my barrier. The closer I am, consider I need to accept some value for x, which must be greater than or equal to 0. So when I try to go into this direction, minimizing, I can never cross the 0 because, of course, I will penalize my minimization problem, giving an infinite weight for it. So it will never consider like this negative side of my space. Okay? And the opposite happens when I am solving a maximization problem. So I am reducing my variable, and every time I reduce it, I will penalize, leading to minus infinite, my objective function, and that's going to be an issue for me. Okay, so I am trying to maximize, but somehow this function just brings such a negative influence that I try to never touch the boundary, and the boundary lies exactly on 0, on the value 0. Okay, so what people does with those barriers, we're going to see now. Okay, at this point, it's nice to mention that Fiacco and McCormick in 1968 studied the barrier approach, and they designed this approach using log functions. But actually, it could use like other functions, but that's typically the way we solve that. Okay, we solve this kind of problem. Again, this is for minimization. When I approach 0, goes to infinity. And for maximization, when I approach 0, goes to minus infinity. And of course, I'm trying to maximize. This is the way of plugging our variables in our primal and dual problems. It's quite easy. You're going to see that it's not difficult. I'm going to go back. Just remember, take a look. All x's must be greater than or equal to 0. What can I do? I have 4 values for x. I have x1, x2, x3, and x4. What we do is plug a sum of a log of x1, x2, x3, and x4 over here. And I give a weight for those logs. So what I'm doing basically is summing up some penalization function. So I am penalizing in terms of x1, x2, x3, and x4. Of course, this me has to be a relevant number, because if it's 0, I am accepting every value for x1, x2, x4, x3, and x4. And that's going to be a problem. What is nice about this barrier is that now we do not depend on the constraints for variable x anymore in an explicit way, but actually they are formulated in terms of my objective function. That's really nice. what happens with my dual problem is the same. Here I was maximization. I am maximizing actually. So when I sum up, take a look. Sum up, this is going to affect my maximization. Just remember, this is going to be simply log of something. So I try to maximize when I approach a given point that assumes the value I cannot accept in my solution. My solution is led to minus infinity. So all this is going to be minus infinity if I approach somehow the value of 0 that I can't accept. In the maximization, it's going to happen the opposite, minus log. So when I approach 0, I go for positive infinite. And of course, I'm trying to minimize. So I don't want actually to go too close to 0 in this case. So that's the way we can come up with barriers to never touch the constraints. And actually, we don't need the constraints being explicitly formulated here no more. Okay? Anymore, actually. So, and the rest is the same, like the subject to, subject to. Now we have our primal and dual problems using barriers. What can we do as a next step? Our next step is to solve this problem. To solve it, we need to build up the Lagrangian functions. So the first point is build up the Lagrangian functions, of course, plugging the constraints. So here I will have ax minus b, it has to be for the equality, ax minus b times pi. My Lagrangian multiplier here is going to be my variable in the dual form. On the other side, this constraint must be equal 0, so pi a minus e minus c equals 0, which is in here, multiplied by my Lagrangian multipliers. And my vector with the Lagrangian multipliers in this dual form is going to be my variable in the primal problem. Take a look here. So nice. That's quite nice. If you don't get it, just go back a few videos and they're gonna remember that. Okay, I just told you that I'm going to use negative here and negative here. Okay, and negatives as you can see here for my constraints. Just go ahead with that. We're going to find the solutions. Of course, you can see later that for this minimization I could use a positive here, but that's actually if I do that, I need to multiply my objective function by -1, all this actually by -1, so it's not necessary at this point. I discussed that before, like several videos ago, I just don't remember. Next, yeah, that's what I told you guys. Primal variable x are the Lagrangian multipliers of the dual problem. In dual variables, pi are the Lagrangian multipliers of the primal. And that's so way interesting. At this point, we need to differentiate our Lagrangian function, starting with the differentiation of our primal in terms of x. When I differentiate in terms of x, let's consider we have x1, x2, x3, and x4, or in general way, xj. Okay? So differentiating this Lagrangian in terms of a given xj, I will find some solution for this differentiation in terms of xj equals 0, and then I will differentiate this again in terms of pi, for a given pi I, and making it equal 0. I will do the same for the dual, differentiating in terms of all my variables. Of course, I have z, so all z's. I have pi's, so in terms of pi's, and I have x's, so in terms of x's too. Okay? After having this differentiation, this, and this, all 5 must be satisfied. If I satisfy all 5 differentiations, I have the solution for my primal and for my dual problem. So what this means is, okay, we're going to find the solution for the primal feasibility, remember guys, for the Cauchy-Tucker condition, the dual feasibility, which are related to my dual constraints, and the complementary slackness, which is a connection we are going to have in the primal and dual problems all together. So we are going to find a way, basically, going back, a way of a way of connecting that. Having this point in the primal space, we're going to have this correspondent point in my dual. When I walk like this and find this point, I have this point in my primal, and so on, until finding the solution. So that's what we are doing, actually. Yeah, not trying, but doing. Okay, at this point, we start the differentiation. So start with the differentiation of this primal Lagrangian function in terms of xj, which is a scalar value inside my vector x. Differentiating in terms of xj, we are going to have, of course, the correspondent cj that's multiplied by that xj. So it is in here. Okay? Of course, from this, I am going to start with this guy here. I think it's just easier. If I differentiate in terms of a given xj over here, that xj is going to be multiplied by a complete row of my matrix A, whose index is I. Okay. For actually along all rows, actually, sorry, and fixing a given column J. So I will vary I from 1 to n along all rows of matrix A. Yeah, that's right. And of course, this is negative. So a negative is kept over here. Differentiate in terms of B, no, nothing, it's going to be 0. And differentiate in terms of this sum, of course, the derivative of log of xj is going to be 1 over xj. So this is going to be me times 1 over xj, and that's the same as me over xj. And that's 0, okay? Of course, I'll have this in terms of x1, x2, x3, and x4. This, okay? On this side, when I differentiate in terms of zj, I will have what? This in terms of zj is going to be 0. This in terms of zj is going to be 1 over zj. So me times 1 over zj is going to be minus me over zj. Plus this part over here. Of course, I am differentiating in terms of a given zj, which happens once inside this vector, and this is minus is going to be plus that particular zj times x. Differentiate in terms of that particular zj, I have xj positive equals 0. And from this equation, from this simple equation, we are going to find something that is amazing. Take a look. This xj I will just bring on the right side, so I have minus me over zj equals minus xj, and that's the same as me equals zj xj for all possibilities of j, of course. You know what's interesting? Please, guys, pause the video here. Go back to the Cauchy-Tucker conditions. You guys will see that this is exactly our, remember, slack variables times x must be equals 0. If you go back in the Cauchy-Tucker conditions, you're going to find that slack variables times x must be equals to 0 to find the perfect solution for my linear optimization problem. Please go back. and compare, you see that this is actually what we refer to as the complementary slackness. Exactly this. It's so nice. Yeah. That's actually the way of connecting the solutions. It's not difficult to see now that when we differentiate the primal in terms of x and the dual in terms of z, we've got a connection. We've got me connecting this side with this side and vice versa. So this me represents a way of connecting the primal space and the dual space in attempt to find the same solution. The same solution. Now I'm going to give another step, and actually I'm going to substitute this me over here by this x j times zj. Of course, if I bring xj times zj here, I can simplify and this will become zj simply. Okay, and that's what I'm doing in this this slide. Okay, just providing that substitution. Me is equal to this, substituting me over here, this me over here, of course, it's going to be zj, xj, simplifying, dividing xj by xj, I have zj over here. That's just a simplification, okay? Why I'm performing this simplification? Because after we're going to build up our problem and solve it in such a general way that you guys can apply our algorithm in any other problem. That's going to be really nice. Our me is also called me complementary slackness. Take a look. Me is basically what? A way of connecting our primal and our dual problems to find the same solution. Wow, so nice. Me has also another name. It's also referred to as gap. This gap tells me if we've got something called the strong duality. What means the strong duality? I have the strong duality if gap after several iterations, this approaches zero. If this product of my select variables by x approaches zero, I will have my strong duality. Actually, that means, take a look here, that I will not have slack variables being summed up to satisfy my primal visibility, my primal constraint. Take a look, this is the primal constraint actually. And I will not have, of course, if this is zero, of course, approach is zero, of course, my product of slack variables times x, that means I don't need slack variables because I'm touching the precise constraint. So there's no need for relaxation. So nice. Okay, but here, some people may come up with a question here, which is why we don't set me equals zero since the beginning. Actually, if we do that, we never find the solution. You know why? Because the barriers, we need to control the barriers. We need to start with a given value for me, like we never get too close to the barrier. But of course, after some iterations, I need somehow to make me just decrease somehow me. If I don't decrease it, I will give like such importance to the barrier term that I will never get close to the constraints if necessary. Again, if necessary. So along the iterations, I need to decrease me. And in this particular linear optimization problem, I need, of course, to get close to the barrier. Why? Because the solution lies on a vertex. Remember, the solution lies on a vertex. So I need to get close to it. Differentiate in terms of pi, this guy in terms of pi, take a look. In terms of pi, 0, 0. And here, of course, I will have ax minus b. And of course, when I differentiate in terms of pi here, of course, this is negative, of course. I will end up with, I just opened up here, just decide to open up. because I'm differentiating in terms of a pi I, a given value, a given scalar inside this vector pi. Okay, so of course, if this guy is multiplied by x, by ax, it is multiplied along the row. I get like all elements of that particular row. So I need to vary j over here to go along all elements of row I, as shown here from 1 to n. And that's going to be all terms of that particular row times xj equals to bi. Okay, so this is the differentiation in terms of pi I. Here, if I differentiate in terms of pi I, I'll have the same solution. Interesting. It makes sense. Actually, you know what, guys? Here, this is a Lagrange multiplier, which Lagrange multiplier in my primal form, which is my variable, my main variable in the dual form. If I differentiate in terms of it, of course I get the primal visibility or the primal constraint. It is here. In terms of a given row, of course, a given constraint. Okay, I. Over here, take a look what happens with the dual form if I differentiate in terms of pi I. I will have the same primal visibility or primal constraint. So I have the same primal constraint. This tells me something really interesting. Even though I have my dual problem, if I differentiate in terms of this pi, which is my main variable, I will get the constraints of my primal problem. The constraints of my primal problem. Something to think about, okay? Okay, and now I'm going to give another step. I'm going to differentiate. My dual problem has another variable, has x. So when I differentiate in terms of x, now take a look at what's going to happen. So differentiate in terms of xj, so xj over here. Of course, this does not make like any difference, but this makes, because I have xj over here, and it's a negative sign. Of course, I have pi a x, but differentiate in terms of xj, it's going to be pi a, and of course, in terms of that particular xj. And that particular xj is going to interfere in my differentiation in this way. I will have the sum of aij pi j. Okay, I just brought like pi in front, like transposing a, just making it like easier to bring this guy over here as the typical application of a matrix basis change on top of pi. So aij pi j varying I from 1 to m. So I'm just walking on a column, on a given column j, okay? That's of course minus zj, because zj is going to be multiplied by xj, and of course minus a given cj that's going to be multiplied as well. Okay, so of course I'll have this negative guy here, and then I'll get this as my result. You know what's interesting? Let's, not in this set of slides, sorry. In the next video, you guys will see the whole solution. And then on top of all those differentiations, we're going to find how our algorithm must be written. And then we write our algorithm, and then we solve it. Okay? See you guys in the next video.